Okay, so we are solving exponential equations. So week 7 and 8, we're kind of splitting up the chapter on exponential, where like last week we were focusing on just kind of looking at what they are and mostly just the properties of logarithms, not really going into the solving part. That's more of like this week. So we're just kind of trying to split that up so it's not too overwhelming. So if you're going into engineering, you're going to be solving exponential equations a lot. You're going to see these a lot. You're going to see Euler's number E a lot. You're going to be doing logs and natural logs. It's going to show up a lot. So really important stuff right here. So well, first let me start with what an exponential equation is. It is an equation where your variable is in the exponent. So this is different from our polynomials where the variable is the base and then the exponent is a number. They both contain exponents, but what is in the exponent is what matters. So exponential have the variable in the exponent. And there are basically two ways that we can solve this. So we can solve it using the one-to-one property, or we can solve it using the inverse property. And the inverse property I talked about in my video last week when I was talking about the basic properties of logarithms. Generally, we use the one-to-one property if you have two exponential equations or expressions set up equal to each other. Their bases are the same, or you can put them so that their bases are the same. But that most of the time that is not true. So when that's not true, we use the inverse property. And the inverse property is sort of like how when we learned about quadratic equations, you learned how to solve by factoring, and you learned all these different types of solving, but not all of them worked every time. Like factoring, you can't always factor, so then you have to try a different method. But the quadratic equation worked every time. This is the inverse property is like that. One-to-one property doesn't work all the time, but when you can use it, it's very easy. But the inverse property works every time. So it's a similar type of situation where one is good and quick when you recognize or you see it's in that form. Otherwise, you have to do the other method. So I'm going to start with the one-to-one property. I've got lots of examples, and then I'll go into the inverse property. So the one-to-one property, and in our textbook, they call it the equivalence property of exponential expressions. Other textbooks call it the one-to-one property. So I have both here. One-to-one is much quicker than equivalence property of exponential expressions. Basically, what it says is if you've got two things, two exponentials set equal to each other, if your base, the thing under the exponent, is equal, then your exponents must also be equal. It's that simple. It's just, well, if the bases match, then the exponents must too in order for these things to be equal. So I'm going to start with an example, and you look at this and you're like, well, wait a minute, it doesn't look like that. So I'm going to write down, we've got, actually, I should use B to write the actual property. If you have b to the x equals b to the y, then that means x equals y because the base is the same. So we've got 3 to the x, but on the right side, we don't have 3 to some exponent. But we can rewrite 81 so it is 3 to some power. So I'm going to rewrite, the left side will stay the same. We're going to still have 3 to the x. 81 is 3 to the 4th power. So we're going to rewrite this as 3 to the 4th power. So now we've got 3 to the x equals 3 to the 4, and you can see, well, then x has to be 4 in order for these to be equal. So you basically are just setting your exponents equal to each other, and you get your answer in this case, x equals 4. And you can double check, you can do 3 to the 4th power, that gives you 81. It's really simple when you have something in this form. So this is example of the one-to-one property. You're trying to rewrite your stuff so they have the same base, And then once you have the same base, you set the equations, the exponents equal to each other, and then you either have your answer, like here we got x equals 4, or sometimes we have to do some solving. So let me show a second example here where we're going to solve using the one-to-one property. So it's exponential because it's 5 to the t, so we're solving for t, and t is in the exponent. So we want to rewrite everything so it's 5 to some power, because that's what we've got. We've got 5 to the t. And on the left, we've got a cubed root. So this is where knowing that the cubed root can be rewritten as an exponent is very helpful, and knowing how to convert from a root to an exponent. And when you have a root, it's the 1 over whatever power. So in this case, it's a cubed root, so it's going to be 1/3 power, 1 over 3. So we're going to rewrite this as 5 to the 1/3 power. That's the same thing as the cubed root of 5. And then you can see, well, if these are equal, then 1/3 has to equal t. And that's your answer. So these are pretty simple ones, but sometimes there is more work that we have to do. So here, our exponent, we're having a base of 5 again, but we've got 2z plus 2. So that's more complicated, and we're going to have to actually do some solving here in addition to just setting the exponents equal to each other. So with the thing with the exponent, 5 is our base. So we want to rewrite the 625 so that it has 5 to some power. Now, off the top of my head, I don't know what power that is. So I would start by doing a factor tree. Like if I don't have it memorized, I do a factor tree. So I know that 625 can be divided by 5 because it ends in a 5. That's one of the rules. So I'm just going to pull out my calculator. And so that 5 times 125 gets you 625. Now, 125, I know that 25 goes into that. That is 25 times 5. And I know that because I'm just thinking quarters. That's 5 quarters. And quarters are, 5 quarters is $1.25. So that's how I know that one. And then 25 is 5 times 5. So all of these are ending up in 5s. So I've ended up with 4 5s here. So 625 is 5 to the 4th power. So I'm going to now rewrite this so that I have it equal to 5 to the 4th power instead of 625. Now that I have the same base, I set the exponents equal to each other. So I have 2z plus 2 equal to 4. And now we do have to do a little bit more solving because we don't just have z equals. We actually have a linear equation that we need to solve. But everything always goes back to linear at the end. We learn these different ways of solving, and we always eventually make them linear. So I just need to subtract 2 from both sides. That gives us 2z equals 2. And then I just need to divide both sides by 2. And then I get z equals 1. It is a funny looking z. There we go, that looks a little better. So the hardest part of this is probably just rewriting the number as some exponent and knowing how, what you're supposed to rewrite it as. You're always looking for whatever your base is on one side that has the variable, you want to use the same base on the right. So your default would be to just keep dividing by that number so you can figure out what exponent it is. But that's the hardest part. Then once you set the equations equal to, or the exponents equal to each other, then you're just solving. So are there any questions on this example or the other two that I've done so far? Okay, so this is the one-to-one property. It's really nice, but it can't be used all the time. When it can be used, it doesn't take long. Not really, but it doesn't work every time. So the other rule that we have is the inverse property. And so this is one of the basic properties of logarithms. One of the reasons why we covered all the properties of logarithms before we went into the solving is so that you're familiar with these properties. And the thing about this property that's important is that if you have the log of something, if it's the base of the log is the same as the base of the exponent, they cancel out and you're left with whatever let me say that again. If the base of the log is the same as the base of the exponential, then the bases cancel and you're left with the exponent. That's basically what the inverse property says. So what we're going to do is we're going to get rid of exponentials by taking the log of both sides to the base that will cancel it out. And then we'll be left with just the exponent, and then we can go from there. And this process of using this inverse property is called solving by using logarithms, because you're basically going to take the logarithm on both sides. So it's like how we can take the square root of both sides. You know, you can add, you can subtract, you can do all these things on both sides of the equations. We can also take the logarithm on both sides. So it's a new action that you're learning how to do. So there's 4 basic steps. The first is to isolate. So that means you want to get the exponential part by itself. So if you have like b to some power, you want to rearrange it so that is by itself on one side and then everything else is on the other. Once you've done that, you take the logarithm on both sides. So that's the logarithm step. And I accidentally pluralized that. Take a logarithm, and you're going to want to use the base b. And you don't actually have to. You don't have to do the same base as what's there. And actually, most of the time I don't. I usually do a log or a natural log. You'll get the same answer even if you try to do it with the specific base. What matters is that you use the same base on both sides. So if I do a log on the left, I need to use a log on the right. I can't mix and match a log and a natural log. So whatever you do on one side has to match the right, but it doesn't matter whether you do a log base 10, log base 5, you could do the natural log, which is base e, it doesn't matter. So I usually do whichever one I have a calculator button for. So my TI-30X that I use has a button for both. So it really doesn't matter whether I use a log or a natural log because both of them have buttons on my calculator. But like my graphing calculator that I use when I start doing calculus and everything, I only have a natural log button. So then I'll do the natural log because that's what I have a button for. So it doesn't matter which one you choose as long as you do the same thing on both sides. So that's the logarithm step. Then you use the power property, and that is one of the other properties you learned about last week, where let's say you have the log of a to the x. That exponent can go in front, and that's x times the log of a. So that's the power property. And so we're bringing down the exponent and putting it in front. And that's why we solve doing this way. Because if you can take the log of both sides, then that allows you to use this power property so that the x, the variable, is no longer in the exponent. And then it's something that you can actually do things with. And then once you've done that, you just solve. And you just solve for x or t or whatever your variable is using the same techniques that we know. Add and subtract on both sides, divide or multiply on both sides. The same solving steps that we've been basically doing the whole class. So I'm going to start with this example. So at first glance, you may think, oh, this looks like it's in the same form as something that we could do the one-to-one property with, but we can't because 70 is not a power of 2. If it was 64, we could use the one-to-one property, but it's a different number, so we can't use the one-to-one property because I cannot rewrite 70 as to some exponent there. So we're going to solve by taking the logarithm. So we already have, the first step is to isolate the exponent part and the exponential, and that's already by itself. So that's already by itself, so we don't have to do that first step. The second step is to take the log on both sides. So what do you guys have on your calculator? So the calculator that you have with you, if you have one that's handy, do you have a log button or a natural log button? Because I will use whichever one that you guys have.
I'm using a TI-30X2S calculator.
So you've got both of them.
Yes.
I got both of them too.
You've got both, okay. Do you have a preference then, if everybody has both buttons?
Since we've got both buttons, can we do it both ways?
Sure. Okay, Tina says hers log has an n above. Yeah, if it says ln, that's the natural log. So Tina looks like she has both. Let's do both. Let's do that because we have the room. We can do both, and you can see how you'll get the same answer. So I will split this up. And we'll do it by the log, and then we'll do it by the natural log. Oh, and you also have an ln button, so it seems like everybody does have both. So I'll start by the log, which will be base 10. And so we take the log of both sides. And so I usually end up writing my stuff in cursive so it doesn't look like 1, 0, it doesn't look like numbers. So we're taking the log of 2 to the z. And then we also have to take the log of the other side, or the 70. So I have the log of 2 to the z equals log of 70. So that's what it means by taking the logarithm, as we're literally writing the log in front of what we've got. And then that exponent, the power property, allows us to drop that z down in front so that we have z times the log of 2 equals the log of 70. And then we're solving for z, so we want to divide by the log of 2 on both sides, because that's basically, if z times that, we want to get rid of it, so we're going to divide. So I'm going to divide by the log of 2 on both sides. So if you're asked for the exact answer, your exact answer would be the log of 70 over the log of 2. But most of the time, you're going to be approximating. And we usually, when we work with logarithms, we usually round to 4 decimal places. So when you approximate, it's a little curly equal sign. So on your calculator, you just take the log of 70. You have to do these separately, because otherwise, if you try to do them together, sometimes the calculator thinks you're trying to divide by a log and it does all this crazy stuff. So do them separately. So I have 1.8451 when I round my log of 70, because it's 1.84509, and I get 4 decimal places at the 0 because it's a 9 after that I have to round up. And then you're going to take the log of 2. So that's 0.3010. And then you're going to divide those. 1.8451 divided by 0.3010. And then that gives me 6.1299 when I round to 4 decimal places. So that's our answer. And with logarithms, you rarely get whole numbers. So and they cannot be written as fractions. They're irrational, so we have to write them as decimals. Yeah, Matt, you have a question.
Yeah, so it's maybe a little more fussy, but if you do like you said, do the logs separately on the TI-30X calculator, you can do it and then save your answers in the stow function. It actually comes out to 6.1293. So that 3 versus 9, how much of a difference is that going to make?
That is a good question. 1 point. Yeah, that is a good question. So usually Alex does tell you specifically to round to a certain number. If we were to round to 2 decimal places, we'd get the same answer. I think if we added an extra decimal place, we might be okay, because this is an excellent question, actually. So let me redo my log of 70 and add decimal place. So that would have been, actually, if I add, that would be 0.9, but then it still rounds up. And then
The reason I asked this one is because there is a rounding error there. But two, I'm a machinist by trade, and so something like this, using those kind of numbers in my trade, that, you know, what, 7/10 or 6/10 off could mean in or out of tolerance.
That is a good point. So if I add 1 extra decimal place, I do get the 6.1293.
Okay. Would Alex accept both ways?
It should. If it doesn't, that's something where, you know, on the, you know, like when you, on your final exam, when you submit this, we can give partial credit for. I think if it asks for 4 decimal places and you do 5 in their intermediate calculations, you should be okay.
Okay.
And you should end up then with the same, because I did 5 here, and then that got me basically the same rounded to 4 decimal as if you didn't round at all.
Okay.
So let's write that down, because this is a very good question, and it's more of a thing to worry about when you're on the computer. In real life, you generally, you know, if you'd have like a calculator to kind of do as much as possible at once, so you wouldn't be rounding. Let's say if it says to round to a certain number of decimal places.
I would like to add one other thing because I know with the calculator in question, the TI-30X, if you do the log of 70 and you actually close the parenthesis on the right side, you can divide log of 70 divided by log of 2. If you don't, where you were talking about the error, if you do log of 70 and you only have the left parenthesis and then divide, that will cause your error.
Okay, that's a good clarification, because I know that I've seen people get the wrong answers, and it's usually because of something like that. So that's why I say do it separately to avoid that. But that is very good. Make sure you close your parenthesis if you're going to try to do it all at once. So
yeah, if you don't write your equation properly in the calculator, it won't calculate properly.
Exactly, and it's user error, not calculator error. So like if we were, you would have to make sure you have parentheses around the 70 and close that parenthesis before you hit the divide button to do the log of 2. So for those who are listening, that's what Matt's saying, is that you will get the same answer if you type it in, but you have to have those parentheses and make sure you close your parentheses, because if you don't, then it's not going to calculate properly.
I've just ran into that error in the job site, so it just
and then that is really important to point out, because it's you have to know how your calculator works, and you have to kind of understand what you're trying to do here to know whether, well, that doesn't look right. But yeah, that's very good.
Thank you.
Yep. So let's do the same problem with the natural log. And we'll follow this new, the rounding rule that I wrote down on the right. We're going to use 5 when we calculate, just to see if we're going to get the same thing at the end. So we're going to use the natural log here. So instead of log 2 to the z, it'll be the natural log 2 to the z, and then the natural log of 70. But all the steps are basically the same. So I mean, it's just a matter of pushing different buttons on your calculator, because you're still going to have z times the natural log of 2. Instead of log, it'll be natural log. And then the natural log is 70. And then you divide both sides by the natural log of 2. So you can see the steps are almost exactly the same. And so we get z equals the natural log of 70 over the natural log of 2. So I'm going to do this separately around to 5 decimal places. And I'm going to use my natural log button instead this time. So that gives me 4.24850 when I use 5 decimal places. And then the natural log of 2 is 0.69315. And so I'm going to divide those. And I get 6.1293 when I round to 4 decimal places. So we got the same exact answer. You know, it'll be slightly different decimal places, but with the rounding, it comes to the same answer. So whether you choose to use the log button or the natural log, it doesn't matter, because you'll get the same answer in the end. And of course, you do have to worry about that rounding, but if we use this rule, if we want to 4 decimal places, if we use 5 in the calculation portion, it works out and we get the same answer. So are there any questions? Okay. So we're really going to be getting into all the different things you can see when you're solving and then having to take the logarithm. So first step is always to isolate the exponential part. So we want to get the 23 to the y by itself, which means that we need to subtract 6 from both sides. So that will give me 795 equals 23 to the y. So now we've got the exponent part by itself, the exponential. And so you get to choose whether you want to do the log or the natural log. Anybody have a preference for this particular example? Let's do the natural log, just because that's the one I tend to use. So we're going to take the natural log of both sides. So I'm going to have the natural log of 795 equal to the natural log of 23 to the y. And then that y drops down in front. So we end up with the natural log of 795 equals y times the natural log of 23. So you can either use like the dot to show that's y times that, or you can put it in parentheses. But I always like to make sure my variable is in front so it doesn't look like the variable is inside your log part.
Yeah, kind of a silly question.
Yeah, go ahead.
Is there ever a time that you use natural log over log, or that you could use them together?
You will never use them together.
Okay.
But there are times where you want to use the natural log. So if your exponent part has a base of e, So if it's e to some exponent, for sure use natural log, because then it will completely cancel out the e. Actually, my example after this, it's 10 to some exponent. So if it's 10, you want to use the log, because that's the same base as the log. But if it's not 10 and it's not e, it doesn't matter. You can, and honestly, it doesn't matter even with e, but one is easier than the other.
Okay.
And that's not a silly question. That's actually that's a very good question.
I just didn't know if I had missed it from previous lessons.
Nope. Nope. So let's see where we're at. We want to solve for y. So I'm going to divide by the natural log of 23. So we're going to have y equals the natural log of 795 divided by the natural log of 23. So I'm going to round to 5 decimal places again. 6.67834. And then 3.13549. And then I'm going to divide those. That gives us 2.1299 when I round to 4 decimal places. Now, just to verify, if I did the natural log of 795, if I do it all in one step, so if I have the natural log parentheses 795 divided by natural log parentheses 23, making sure I close my parentheses so that I do it all in one step, we get 2.1299 with 4 decimal places. So confirmed that if you calculate with 1 extra decimal place, when you round back to the 4 you might be asked for, it will match even if you did it all in one step. I just wanted to double check that that worked with another example just to be safe.
I did it the other way with log, and it works out the same.
Okay. And if just in case you're not good at rounding, so I'm bringing the Desmos scientific calculator here, and the scientific calculator does have the natural log and the log button, but it also has a round button. So if I could even, let's see, I could do natural log of 795, make sure I close my parenthesis, divided by natural log of 23, and then, so it's rounding to a whole number right now. I think if I want 4 decimal, it's a comma, 4, and then you can see that it rounds. So if you're not very good at rounding, instead of using like your physical calculator, because I don't know how to make those round, there's probably a way. I don't know how to do it. But Desmos, the scientific calculator, does have a round button, and you just tell it how many decimals you have, and then it will round it for you. So just, I know sometimes people get really confused on rounding, especially when you've got numbers that round to like 0 and stuff like that. So there is that option. Any other questions or comments? Okay, so this is one where you want to use a log because it's base 10. So because of the fact we have 10 as our base there, we want to use the log because it will just make the calculations easier. You could do natural log, but it's going to be more work. So we want to get the part with the exponent by itself. So I'm going to subtract 4,200 from both sides. And I'm not going to do that in my head because I'm probably going to mess it up with all those zeros. So we're going to get 10 to the 5 plus 8x equals 79,800. And now we're going to take the log of both sides. So sometimes what I do is instead of rewriting it, I will just kind of write it in front to kind of squeeze it in. And then the log cancels out that 10 because the log 10 of 10, the log base 10 of 10 is just 1. So those cancel out and we're just left with 5 plus 8x. That is the inverse property. The log of 10, base 10 of 10 to some exponent, those cancel and you're left with your exponent. So by choosing log, we could just cancel out that left part altogether and just have 5 plus 8x. So we've got 5 plus 8x equals the log of 79,800. And now we're going to solve for x. So I'm going to subtract 5 from both sides. Now the 5 cannot be subtracted by the log part because that number is connected with the log. The log is an action on that number. So we still have the log of 79,800 and then minus 5. So those are separate. That minus 5 is not part of the 79,800. If it's helpful for you to not get confused there, you could do the log of 79,800 right away so that you don't get confused. So instead of writing that log, I can do that on the calculator and then round it to, let's use 5 decimal places again. So that'd be 4.90200. And then when you subtract 5, you can subtract 5 from this number because you've taken the log of it. So if you take the log immediately, then you're just with that decimal that you're working with. And that gives us negative 0.0979. Oh, that's another 9, which rounds us up to 0, which rounds that up to an 8,800. So you could either leave it as saying log is 79,800 and then just pretty much write what you're doing, or you can take the log and work with the numbers. It's kind of up to you. But once you've done that, then you want to divide both sides by 8. And so that gives me negative 0.01, and I'm going to round to 4 decimal places. Negative 0.0122 when I end up dividing that by 8. And that's when you're working with decimals. If you wanted to keep it in the exact form, we would have that log of 79,800. Then we subtracted 5, and then we would be dividing it by 8. So if you had it in its exact form, it would look kind of messy. But then you just basically plug it in your calculator, and I'm actually going to do that all in one step. Make sure that all your parentheses are in the right places. Did I? Oh, I think I accidentally hit natural log. I'm like, my numbers, well, that wouldn't. Yeah. I accidentally hit natural log, and that does make a difference in this case. So yeah, you get the same answer if you did it in the exact form and then put in your calculator versus rounding and then solving. Just make sure you're going to follow that rule where you maybe use 5 decimal places and then round to 4 at the end. Are there any questions or comments? Tina, did you use the LN button? Because that was my first mistake when I was checking on my calculator. No. Okay. Did you remember to close your parenthesis? Okay. Did you put the whole top in parentheses? Because if you don't do that, your calculator might divide only the 5 by 8 and not the whole thing by 8. Yeah, make sure you have parentheses around the log 79,800 minus 5 before you hit the before you hit the divide button, or hit enter and then hit the divide button. Okay. Yeah, it's that whole parenthesis issue. I know it comes up. So you may want to then use the method on the right where I took the log immediately, basically, and put it in decimal form so that you don't run into that parenthesis issue. So yeah, if you're missing a parenthesis in the key place, then it does change your answer. And negatives, yeah, that's another thing. So it's one of those things where it's like you just have to be aware of it or find ways around it. Anybody else having any issues with putting on their calculator or anything like that? Okay. Sometimes I have students tell me they like to do math in their head, and I'm like, this is not something you can do in your head. Certainly not unless you are like some genius that knows how to take the natural log of stuff in their head. But this one's definitely you need a calculator and to write things down to make sure you're not making mistakes. So, Matt, this one goes back to your question is which one do we use? We see E, so we want to use the natural log. So whenever you see E in there, just automatically use the natural log, because that will just make things easier. So in this case, we have a number in front of the E. We have 80 equals 320, and then E to the negative 0.5t. We want to isolate this part, not the 320. So you do not want to take the log at this part. You want to divide both sides by 320 first. If you do take the natural log at this point, you're taking the natural log of two things multiplied, and then the rules don't work the same. You have to do some extra steps in order to make it work. So divide by 320 first. And, because we're dealing with decimals, it's fine if you want to do 80 divided by 320. And that actually comes out to 0.25, so that's easy enough. It's not like a long decimal. This is like the one time in the class that you're allowed to use decimals versus fractions. So we've got 0.25 equals e to the negative 0.5t. And then we want to use the natural log in this case. So I'm going to take the natural log of 0.25 and then the natural log of e to the negative 0.5t. So the natural log in the e, that cancels, and I'm left with just negative 0.5t. And then on the left, if we want to avoid potential errors and parentheses and stuff like that, then we're going to want to just take the natural log of 0.25 immediately, just to kind of avoid possible errors. And we'll round to 5 decimal places. Negative 1.38629. Okay. So now all we need to do is divide both sides by the negative 0.5 because we're solving for t. And So I usually, you know, because it's I have the answer thing, I can just do that straight on my calculator after I hit the natural log. So I just do the divide part, and we're going to get, as t, we're going to get 2.7726 when you round to 4 decimal places. So you really get 2.7725888722. So we're rounding after the 5, we want 4 decimal places, and that 8 forces us to round up to a 6. Okay, so I'm gonna, oh, let me go back. You have an error. 88722. Okay, that is just part of this line. That was part of the decimal. I drew the line here just to show where we were rounding. So that 88722 was just the rest of the decimal places, and won't divide the -1. Did you close? If you've got an open parenthesis, if you try to take a natural log of a negative, like if you have a natural log in there still, natural logs and negatives give you errors. So make sure that you don't have like a parenthesis or natural log that's still open. It might be helpful to just like clear everything and retype the negative. Okay. If you're struggling with your calculator, you may want to use the Desmos one, just because you know that you can at least see what you're typing in. You know,
improper parentheses can really mess things up.
They really can. Yeah, I'm guessing what might be is you have your natural log of 0.25, which gives you this number. If you hit divide at this time and then do the -0.5, that's where you get an error because you've got a negative inside your natural log. So I'm guessing it's either make sure you hit enter here or close your parentheses so that you actually just got your number, and then do the divided by, you know, -0.5 thing. Or just retype the number on your calculator so that you're not dealing with that. So this is the parentheses can really mess things up.
Can you hear me?
Yes, thanks, Matt. Yeah. So Tina, if you look in the chat, Matt typed exactly what you want to type into your calculator in order for it to work. When in doubt, add more parentheses. That's sort of like if you don't think you have enough, it's okay. Don't worry about if your mic's not working. That's fine.
Depending on what calculator you're using, with the TI-30X, it really works towards, I don't know the TI-84, but it really works.
I have an 83, not an 84. Yeah, I need to see like a picture of the TI-84 to see what's going on with it. I think it's probably the parentheses again. Yeah, I think that's what it is. So, you know, if you're struggling, it might be like, let me not even use the 84 and let me just use Desmos or something like that.
Yeah, just separate your order of operations. Hit enter between each.
Hit enter every time. That's a good one. Hit enter every time when you should be okay. You did. Okay. Then I don't know. That's one where it's like I almost need to be there next to you to see what's going on. And unfortunately, a little harder to do online. Well, I have like more than enough examples, but there is one example I definitely want to get to. So, and it's this one, because we've got exponents on both sides, things with exponents, but the bases are not the same. So it's like, well, what do? Well, you still take the logarithm of both sides. And you just do it at this step because you don't have anything to move to one side or another. So we're still going to do the log or the natural log of both sides. And let's do the natural log. So we're just going to take the natural log of both sides. And then our exponents still come down in front. And you have to be very careful about that because the whole thing in front is the 4x minus 1 here on the left. So it's in parentheses because that's the entire exponent that goes in front. And then the 5x. So it's going to be 5x, like maybe you'll want to put parentheses around there or something just to make sure that that's together. And then the natural log of 3. So we're trying to solve for x, and we've got x on both sides. And the problem with having x in parentheses is that we have to distribute. So I have to basically distribute this natural log of 7 through the parentheses there so that I can get the x outside of the parentheses. So before we do that, let's convert these to decimal values. So I'm going to take the natural log of 7 and round it to 5 decimal places. And then I'm just moving it in front so it looks more like a regular distributive property. And then I'm going to do the natural log of 3. So that's 1.09861 and then times 5x. So we're really working with the decimals here. And I'm going to distribute on the left 1.94591 times 4 is 7.78364x. And then I'm going to multiply it by -1, so that's -1.94591. And then on the right, I'm going to multiply the 1.09861 times 5. And so that gives me 5.49305x. Can't forget my x there. So now I'm solving for x. And I know it looks messy because we've got all these decimals, but the solving steps are the same. I'm going to move the x that's on the left to the right so that I have my x's on the same side. So I'm going to subtract 7.78364x from both sides. So I got -1.94591. And then I got my 5.49305 minus 7.78364. I got -2.29059x. I'm going to divide everything by what's in front of the x, so the -2.29059. Sorry. All right, -1.94591 divided by -2.29059. We get 0.8495 when I round to 4 decimal places. So what we had to do extra here is we had to do the distributive property because we had in our exponent more than one term. The fact that we had different bases really doesn't matter because you just convert them to your decimal form. That's not a big problem. It's we've got the multiple things in the exponent that gets a little tricky, is that you do have to just distribute first. And it's easier to distribute when you convert to the decimal versus leaving it in the natural log of 7. It can kind of get a little confusing if you leave it in that form. So this is basically the method you're going to be doing most of the time for those going into engineering is going to be solving by taking the logarithm, which is why I spent most of this lesson on that, because that's the most common thing that you're going to be doing for those going into engineering. Anyone else not going into engineering, you're probably not going to see this stuff again. It's just good practice in your problem solving skills. Yeah, in business administration, you're unlikely to have to deal with this. You may be dealing with natural logs, just trying to rescale graphs. Sometimes what we'll do is, instead of having, if you're dealing with really big numbers, instead of just doing a regular graph, we'll do like a log graph where we change either the X or the Y axis to be the log of the number instead, because it makes really big numbers smaller and easier to graph. So it's possible if you're going into business administration, you might see that, but it's unlikely you're going to be solving any taking the logarithm. This is one topic that's very specific to those that are really going into engineering, where they're going to have to do this a lot. So, well, thank you guys for coming. This is the last live that our term ends on Tuesday. So, hopefully things are you're ready to get in the rest of the stuff, and you'll be all set to finish out. Just as a warning, because the course will cut off all access at 11:59 p.m. Central, don't wait to the last minute to get in your final exam. If you wait too long, you may be cut off on time if it's too close to the due date, or you may not be able to submit your work if it's too close and the course closes. So you really can't have anything late this week. You're going to want to make sure you start it soon enough that you have your full, I think it's 2 hours and 15 minutes. So you want to make sure you start the exam soon enough that you get a full 2 hours, 15 minutes, plus time after that to scan or take pictures of your work and then upload it. So just as a heads up, it's not something that you really want to wait to the last minute for that. All right, well, I'm going to let you guys go. And yeah, you guys have fun. Bye.